See that? Right? There we go. The only other thing I need to do is rewrite everything in terms of tangent. So that's already tangent, right? This, though, don't go say it's du, because we're already using this as du, right? So you can't say du, then you have du squared. What the heck's that? We've never had that, right? Yeah. So let's use the Pythagorean identity on this one.
Tangent squared plus 1.
Tangent squared x plus 1. So this is going to be, I don't need the parentheses around the first one. This is going to be tangent to the fourth x, parentheses, 1 plus tangent squared x, that's secant squared x, and then secant squared x dx. And then you can rewrite everything in terms of u. So you get integral. Yeah, we'll distribute. I'm going to go u to the fourth right now, and then 1 plus u squared. I'll distribute on the next step. Is that all right?
Yeah.
Or I should say, you will distribute on the next step, dot, dot, dot. At this point, you can take it because you're just going to go, what, u to the fourth plus u to the sixth? The antiderivative of that is 1/5 u to the fifth plus 1/7 u to the seventh, and then replace u with tangent and add a plus c, and you're done. So a slightly different sort of technique there, right? We peel off a secant squared, take advantage of the fact that the derivative of tangent is secant squared. We good? Sure?
So what do we do if we get odd?
Yeah, let's see what happens if we get odd. I'll have to go look at my old exam 2s for this class and see if I actually give any trig integrals at all in the test. If I'm not mistaken, you're not going to see a single, well, you might see one trig integral where it's what we've done today, but most of the time it's going to be built into the trigonometric substitution problems. So you'll get to that eventually, but you got to do some other stuff first. So we're laying the groundwork here for the next part of the section. Okay, so let's see. If we have a tangent to the m, secant to the n, with n being even. So if we have an even on the secant, we're going to factor out a secant squared. We use the Pythagorean identity, let u be tangent, and then make the substitution. Right? That's what we just did. Now let's do an odd one. Integral tangent to the fifth x secant cubed x dx. That's a cubed. This is a random question. I usually wouldn't ask my students this, but has anyone ever done painted furniture with a spray gun before? Is anyone in here? You have? Yes? Did you prime it? Did you use a primer? Did you spray the primer? Was it a water-based primer? Water-based? Okay, maybe I'll talk to you after class. I'm using a shellac-based primer, and I'm thinking of just going to like Harbor Freight and buying a little $13 spray gun and just using it and priming it and throwing the gun away. Because yeah, we'll talk later, maybe. All right. Okay, what do we do here? Let's see, why can't we do sine squared factored out? I keep saying factored out. We're technically not factoring anything. We're just peeling it off, rewriting it. That's what we're doing. Because factoring you only do when you have addition, subtraction between terms and you factor something out. We're just rewriting the thing, all right? But why can't we peel off two factors of sine over here? Or secant, I'm sorry. I would have a single secant here, right? And we don't have a Pythagorean identity for secant to an odd power, so you couldn't get it over to tangent, right? You would never be able to get it over to tangent,
Hey,
But
right?
you could take one off the tangent x and do secant x.
You could do what?
Take one off the tangent and do secant
Okay,
x.
so we could peel a secant x and a tangent x out. See what happens. We could go tan to the fourth x, secant squared x, and then we peeled off one secant and one tangent, and I'm going to write it that way, secant x, tangent x, because it's easier to recognize that, hopefully, as the derivative of secant x, right? So that's the derivative of secant x, which means I've got to rewrite everything over here in terms of secant. That's already secant. Tangent to the fourth, I can use my Pythagorean identity, can't I? It's going to have to be tangent squared squared, though. That's fine, yeah. So I'm just going to write down, right now I'm going to let u be secant x, and the derivative of that will be secant x tangent x dx, all right? So let's get everything in terms of secant. We have tangent squared squared, secant squared x, secant x tangent x dx. Now tangent squared can be written how? Secant squared x minus 1. So you just take this identity, you're solving for tangent squared, you subtract 1 on both sides. So tangent squared x is secant squared x minus 1. All right, there we go. Everything is in terms of secant, except for this last part, but that's okay because that's this, right? That's du. So the new integral is u squared minus 1, that quantity squared, times u squared again, and then du. So u squared minus 1 squared times u squared, that's du. There it is. So what are you going to have to do now? You're going to have to expand this. U squared can't get distributed yet. First expand, right? You have to do exponents before multiplication. So expand that, then distribute your u squared through. Dot, dot, dot. Can you handle it there? You got that? At the end, you'll replace u with secant x.
And it would never benefit us to if there were only a single, get secant alone and then have the square root of tangent squared plus 1.
I know what you're saying. If we just peel off a secant squared, and then we have a secant here, and then solve that, and then take that root in there. No, because, well, actually what you're doing is you're actually reverse engineering a problem that's coming, okay? Because you're going to have a square root of something with something squared in there. Think about that. If you wanted to know what secant x was, right? It's square root of tangent squared x plus 1, right? Yes? So think about this. Let's say I gave you an integral that looked like this. Integral square root of x squared plus 1 dx, and I asked you to integrate that. You have no method for this, okay? There's no integration by parts, there's no integration by parts, no basic u substitution. This is obviously not a trig integral because there's no cosine, sines, or tangents, or secants, or anything like that. But right now, if I make a substitution, I just say, hey, look, everyone, everywhere I see x, I'm going to replace it with tangent u, okay? Everywhere I see an x, I'm going to replace it with tangent u. Then the derivative of that would be secant squared u du, yes? Are you with me or not? Okay, rewrite this problem. What is it? What is the square root of tangent squared u plus 1? times dx, which is secant squared du, secant squared u du. Okay, but what's the square root of tangent squared u plus 1? This is, that's secant u. So this is secant u times secant squared u du. That's secant cubed, right? This is a trig integral now. And so we'd finish it, and then we go back, replace x. Everywhere we see a u, we'd have to replace it with arctan of x. This is where we're headed, but we're not, yeah, we don't do that here, okay? But that's where we're headed. So no, do not do that. Don't peel off the secant squared and go try and replace the secant with the root. It's just going to get more complicated. Okay, we're good, I hope. How y'all feeling about this?
I like not having a lot.
I mean, you actually kind of have steps. If you like steps and processes and techniques, you kind of have like a somewhat of a template to follow. And I even let you have those on the test, so that's, I think, helpful. All right. You're going to have to get your hands dirty with your homework because there's a lot of different variations of this that you need to see.
Yeah, there's a lot of problems.
Yeah, there's a lot of problems.
You see,
It's like 60 problems?
61.
61. I think you can do the first 30 of them for homework because the first 30 covers this stuff and then the next 30 covers the other stuff. I always feel bad, that I'm asking you to do 30 problems, but remember, I did them already. I did them on camera. I mean, so I know what you're going through. I know what you're about to go through. All right, so here's some unusual problems, all right? I say here, there are other cases which aren't as obvious. For some cases, we need knowledge of common identities, integration by parts, or just some persistence. So look at these three. They look very unassuming. This one's on your formula sheet. And I believe I told you in the beginning of class that if you see any of the trig functions, sine, cosine, tangent, cosecant, secant, cotangent, all those, they're on your formula sheet and you have the antiderivative. So someone look on their formula sheet and tell me what the antiderivative of this is. Well, I know what it is, but you look it up. Okay, tangent x antiderivative is equal to ln of absolute value of secant x plus c, right? Okay, that's what it is. Well, let's see why. Okay, let's see where this comes from. This one's actually not that bad, all right? Because all we do is we take the original problem. Now, it's not tangent to a power, is it? Like squared or anything like that. So we can't use any identities. We can't peel anything off because it's just tangent. So what we do is just rewrite it as sine x over cosine x. And once you do this, I mean, we're pretty much there because this is a basic u substitution. What would I let u be? Remember, I need to see its derivative, and the derivative can't be trapped. So u would need to be what? Cosine x. Because its derivative is sine x, well, negative sine x, right? So I'm going to write this. Notice I already moved the negative to the other side. So you all agree with that? Yes. So I can rewrite this integral how? So the sine x dx is going to really be my negative du, right? So why don't I go negative du like that? And I still have the 1 over cosine x, right? So 1 over u. And what's the antiderivative of 1 over u? Natural log of u. So this is going to be minus natural log. And by the way, we need to have absolute value on that antiderivative. I don't think I stressed that enough because a lot of you left that off on the test. But technically, the antiderivative of 1 over u is natural log of the absolute value of u. And that's because of domain restrictions and stuff on natural log. All right? All right, and what's u? What was u? Cosine x. Well, that's not the answer. It's in your formula sheet. Did we mess up?
One has a negative, no, one doesn't.
This one has a, well, this has cosine, that one doesn't.
Oh,
Did we mess up?
1 over cosine is
1 over cosine is secant, right? How the heck do I go from that to 1 over cosine? Absolutely you can. That's a property of logs, right? This is a -1, isn't it? Property of logs says if you have power up here, you can bring the power out, right? But if that means if I have a number out here, I can bring it up. So this becomes natural log of the absolute value of cosine x, that raised to the -1 plus c, not the arc cosine. It's the absolute value of cosine of x to the -1, which means 1 over it. And 1 over cosine is secant. So this is natural log of secant x plus c. Not so bad, right? Once you rewrite tangent as sine over cosine, it's just basic u substitution. I could have shown you all this as an example of u substitution a long time ago. I could have shown that to you, right? All right, let's look at the next one. Oh, secant x. Oh, this one. This one. This one. All right. Let's play with this one for a little while. This is in your formula sheet, but let's not even think about that right now. Any ideas? 1 over cosine x? That seems legitimate. We just did that with tangent, didn't we? Okay. It's up to you. It's not going to get us there, but... Yeah, but I mean, that seems very reasonable, right? What's wrong, though, with this compared to the other one? We don't have a sign, right? So we can't do a basic u substitution because we don't have a derivative of anything sitting anywhere, right? Okay, all right, let's go with integration by parts then. If we do integration by parts, you got to let something be your u and something be your dv. And you really only have, u can only be secant, right? And that dv has to be dx. So the derivative of this is secant x tangent x. I'm still not afraid of this, but v is x, right? So my new integral looks like this. Ultraviolet minus integral, no constants come out, but I have an x, secant x, tangent x, dx. And now what I have is something even more uniquely difficult because I have a power function mixed up with my trigonometric functions. Nothing has gotten nicer, right? So you might try integration by parts again. What would happen, because I saw some students do this on integration by parts, what would happen if I did integration by parts again? This time I let u be x and dv be secant x, tangent x, dx. Derivative of that would be dx, antiderivative of this would be secant x, and basically you would just be undoing what you just did. Do you see that's the reverse of this table? Yeah. And so what you would get at the end is something like 0 equals 0, and it would tell you nothing. You would have no answer here. So you never want to do a substitution, a setup on your table, and then on the next step, do the same setup backwards, because it just takes you back to where you started. But I don't think there's anything else that you would want to do. I don't know. Do you want to do that anymore? We can. It got worse, though. Okay, so u subs out. I think integration by parts looks like a nightmare. So this is a great example of a problem where I'm going to show you the way to do this, and you're just going to go, what? Like who thought of that?
That's
right? And so what you have to do is appreciate the fact that, I mean, this is the way math works. Like, there are problems out there, and there are people out there throughout history who have looked at these problems and suffered through them and struggled and just threw everything they had. You know, woke up in the middle of the night, I think I got it, I think I got it. Shit, you know, went back to bed. And for months and months and possibly years, struggled with this stuff, right? I mean, that's the way it works with a lot of math. I mean, there's just a roadblock, and we're at this roadblock for a long time until someone just has some weird insight. Okay? Pardon?
Is there something that like we cannot solve?
I'm glad you asked that. Yes. Are there integrals that we can't solve? Yes.
Yeah.
A lot of them. In fact, infinitely many that we can't do. One of the most famous integrals that we cannot solve is this one right here. It's only famous because it comes up in probability and statistics. This is part of, you know, the bell curve I was showing you earlier? It turns out that the bell curve, the standard normal bell curve, has a very special property, and that is that it goes forever in both directions. The standard bell curve, if you were to compute the area underneath the bell curve, the area, understand what I mean by area under that? Is exactly 1. And that's important because in standard normal distributions, the area under the curve represents the sum of all of the probabilities of all the events that could happen. So it's like, let's take something like people's heights, okay? Like, let's say we have it like an average height for, let's say, men or something, right? Whatever it is. Well, what's the probability that a man would be, let's say, 6'5"? It would be a lower probability than, let's say, 6 foot, okay? So I don't know what the average is for a man, but okay, whatever, 6 foot. So you have this, right? Now, what's the probability that a man is 7'2"? Very small probability, right? What's the probability that a man's going to be 10 feet tall? You can't say 0, okay? Because it's a probability. There is a chance that a person could be 10 feet tall. Now that might be like the odds of being 10 feet tall those odds might be the same as like winning the lottery every single day for the rest of your life. That could happen, yes? If you played the lottery every day for the rest of your life, could you win every day?
Yeah.
Yes. What's the probability of that happening? Infinitesimally small. So this right here, these are infinitesimally small numbers. All right? But there is a probability. Any probability distribution function must have a total area of 1. Turns out that the standard normal probability distribution involves this function. And so when we integrate it, we need to get 1 on the entire number line, which we haven't talked about that. We would basically be integrating from negative infinity to infinity. We haven't done that. But you still have to take the antiderivative of this, and you can't do it. You can't do it using what we're doing now. You have to use power series. That's the only way you can do it, which is chapter 8. So does that answer your question? Yes. Yeah, you asked, yes. So there are functions we can't do them yet, but that's what makes power series just absolutely incredibly useful. So we'll have a workaround. Okay, so back to this. Somebody's suffering, right? So at some point, there's this very brilliant, and whoever did this doesn't get any like a ribbon or any medals or anything, okay? It's just like, oh, cool, that was a cool way of doing it after they suffered for years and years. Okay, so here it is. They just multiplied it by 1. But look at the 1 that they came up with. Secant x plus tangent x over secant x plus tangent x. So maybe they just woke up in the middle of the night from that dream and were like, yes, that's it, secant x plus tangent. They had been thinking about it and they finally figured this is going to work. That's 1, right? I'm allowed to multiply something by 1? Let's do it. Let's multiply. So this is like secant x over 1. So distribute it. And you get secant squared x plus secant x tangent x over secant x plus tangent x? Now, does anyone see what we can do now after that brilliant use of a hidden one? U sub. What's the U? Not quite.
Secant x tangent x.
Look at it. U is the entire denominator. Look at, let U be the entire denominator. What's the derivative of this? Well, what's the derivative of secant x? Secant x tangent x plus what's the derivative of tangent x? Secant squared x. By multiplying by this very awkward one, you actually get a basic U substitution to happen. Now, you would never be asked to figure something like this out on your own and come up with this one. But I'm just demonstrating to you how some integrals just require some really crazy stuff to make them work. So this really becomes, oh, we need to make the substitution. U is secant x. If you like that sort of challenge, where you would sit there and suffer for a long time, then math is probably something you should consider as your major, because that's what it's about. Yeah, but the reward is so sweet. You know, when you... No, it's that reward you get. I know you all have that feeling when you're doing math problems where you get something right and you get that little kind of adrenaline, little, yeah, I got it. You know, like, yes, I win, you know? I win. So as you move up in math, those victories become less often, but they become that much greater when they happen. It's like, did I tell you about my professor, what he told me about his PhD, his problem he solved? Okay, so I had a guy I worked under who's a very, very bright man, and we were talking about his problem. Because in math, you have to at some point solve a problem no one solved to get a PhD. So to get a PhD in pure math. You can get a PhD in other areas of math, but for pure math, you have to solve an unsolved problem. So, okay, he told me that in order, the greatest moments in his life are his daughter being born, solving his problem, marrying his wife. He told me that. He told me that. So, I mean, that gives you some idea. And he was serious, dead serious, straight face, not joking. Like, no, I would never tell her that. But, I mean, that's the level at which that feeling was so wonderful. I mean, he probably worked on that problem for like 12, 13 years, you know, and then finally got it. Yes?
I saw an article this week that said someone has proof of Riemann's hypothesis.
That would be incredible. Yeah.
What's the hardest problem you've ever done? What's the most rewarding problem you've ever...
I can't remember. I've done a lot. I just remember one problem I couldn't get. That one I can't. That one I remember. But all right, let's finish this. What is this? 1 over u du? So natural log absolute value of u plus c. What's u? That's the formula, right? If you look in the back, secant x plus tangent x, natural log. Very awkward, right? Very, very unusual. But brilliant, right? Brilliant. That's a brilliant use of 1. Yeah, the Riemann hypothesis is one of the, what do they call them, the $1 million questions? I'm very doubtful that it was solved, but that would be huge. Yeah, send me the link. We had a similar thing happen a few years ago with Pascal's, Fermat's last theorem. Someone came out and said they had proven it, but there were only like 2 or 3 people in the world that could actually understand the work, like the guy who did it. And it was proven, but it took a few more years for it to get refined. They found some mistakes in it, and then they were able to fix them. And but the Riemann hypothesis is a big one. That's probably the big one. So I'd be shocked, but hey, that would mean progress is being made. So yeah.
It wasn't that guy from the Geico commercial.
What's that?
It wasn't that guy from the Geico commercial.
No.
Is Riemann still alive?
Mm-mm. No.
How long ago was that?
160-year-old.
Yeah, Riemann, we're going to talk about Riemann in here, not the Riemann hypothesis, because you have to talk about complex numbers. And it's, yeah, so we won't, but we'll do some Riemann. Okay, we believe the hypothesis is true, because we've had computers attacking it, and we haven't been able to find a counterexample. And billions of, like, try, plug this in, see if it works. It works. Plug this in, see if it works. It works. And we've done that billions and billions of times. But just because something happens a billion times, does that mean it's true? How about a billion times? How about a billion to the billion times?
So what is the Riemann sum? Is it that?
The Riemann hypothesis, or the Riemann sum we're going to do. The Riemann hypothesis has to do with figuring out where the roots to a certain function exist, like where they are. They all lie on a line in the complex plane. And that's the hypothesis, but it hasn't been proven. Maybe. All right, so was there another one on here? Secant cubed x. So this one's not so bad, because this one's secant cubed can be done with integration by parts. You go secant x, secant squared x. And then what do you think you use for your u and dv here? Secant x here, because you can differentiate that, and secant squared x here, because you can integrate that, right? And then this becomes secant x, tangent x, dx, and then v becomes tangent x, and I'm getting sloppy here. So the new integral becomes ultraviolet secant x tangent x minus integral, and then voodoo becomes tangent squared x secant x dx. Do you all agree? Unfortunately, this can't go with anything we have. Okay? So what you have to do now is you have to rewrite tangent x as secant squared x minus 1 secant x dx. Are y'all following me? That's Pythagorean identity. So what we have is that integral over there is equal to secant x tangent x minus integral of what? Go ahead and distribute this through. Secant cubed x minus secant x, right? dx. Anybody see it? Let me remind you of where we are here. We are saying that the integral of secant cubed x is equal to secant x tangent x minus integral of secant cubed x dx plus integral of secant x dx. So what I did was I just passed that negative through and split this into two integrals. Do you see it? What is it? What just happened? This integral appeared again, right? Yeah. And it's being subtracted. So I add this integral to this side. This is the rabbit out of the hat. Okay, so this integral is going to come over here. So how many of them are we going to have? If I add that one, it's gone. I get two of them over here, right? Yeah. And now what about the integral of secant x? We just did that, didn't we? Wasn't that natural log of secant x plus tangent x, right? So integral secant cubed x dx is equal to 1/2 times secant x tangent x. Where did that 1/2 come from? I divided both sides by 2. Plus natural log of secant x plus tangent x plus c. So this was from integration by parts. This was that brilliant use of a 1 that gave us that, right? And then the 2 I had to divide through, so I just put a 1/2 there. Interesting. Okay. See if there's anything else on the notes. I think I have just enough time. Okay, next thing is trigonometric substitution. So that's next class. So let me pass around the sign-in sheet. And I'm going to talk about Pascal's triangle, if you're interested. Man, we haven't signed in quite some time. Wow. Whoa. Whoa. Okay. Well, here we go. Sign in for the 24th. Okay. How many of you have seen Pascal's triangle? Yeah, a lot of you? Okay.
It's been a long time.
Okay.
Knowing what we learned in this class, would it be easier to understand the 1 plus 2 plus 3 plus 4 thing? Remember that?
No. It's going to make that more confusing. Because we're not going to accept that here. Yeah, we would say that diverged to infinity in this class. All right, so if you're interested, this goes back to the idea of if you want to take a binomial and raise it to different powers. If you want to go, you're not going to upset me. You're just going to hurt my feelings. Okay, so like these are different, those are all binomial expressions, right? X plus y. So that could be like x minus 2, that could be x plus 3, it could be y minus 4, it doesn't matter, 2 terms. And we want to raise them to different powers. So if you raise anything to the 0 power, you get 1, except 0 to the 0. But I'm going to put the 1 here. And then if you do x plus y to the first power, it's just x plus y, so I'm going to write it like this. And then if you do x plus y squared, we all have probably done that enough that we would be comfortable with the idea that that would be that, right? And if we did x plus y cubed, that turns out to be this. Okay, so you would have to expand it out. That's what it would turn out to be. And let me see. No, I'm just going to have to go to black again here. If we did it to the 4th power, it'd be x to the 4th plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the 4th. This is a pretty cool thing you can do to like show off to your friends. Then you can do like x to the 5th plus 5x to the 4th y plus 10x third y squared plus 10x squared y cubed plus 5x, where am I? xy to the 4th plus y to the 5th. So I'm expanding these. Obviously, I'm not expanding them in my head, right? I'm not, well, maybe I am. No, I'm not. I'm not. Right? I'm not doing x plus y times x plus y. Go, man.
You showed us this is pre-calc.
Go. No, go. No, go. It's fine. It's fine. I'll give you a quiz on it next time. Okay, so this right here, I did show you all this. I remember I did. So I know you're not bluffing here. I know I did. And Cal 1? Really? Okay. Oh, to prove the power rule. This is how you prove the power rule. Okay. So this was discovered a long time ago that there's a pattern here. The pattern is pretty easy to pick up with the powers on the x's. So like if you want to do, let's go to this one, right? X to the 4th power. Look what happens to the x's here. You start x to the 4th, and the next term it comes down. X cubed, then x, then, x squared, then x, and then the x vanishes, right? And then the y's, it goes backwards. The y's, it's not there, then the y is there, then it's squared, then it's cubed, then it's to the 4th. So the x powers come down as the y powers come up. And that happens for every single line. Okay, so if we wanted to do the 6th power here, We know the first term is x to the 6th. Plus, now don't worry about the number yet. I know the next one's going to have, it's going to have a number, but then it's going to be x to the 5th, y. Plus, then I'm going to have some number, it's going to be x to the 4th, y squared. Then x to the 3rd, y to the 3rd. And then some number, x squared, y to the 4th. Then some number, x, y to the 5th. And then last one, y to the 6th. So the only question is to get these numbers, to figure out what the coefficients are. And to do that, you can use this thing called Pascal's triangle, which is somewhat embedded in here. You can see that the first number, the first coefficient we have in the first row is just 1. And then the coefficients in the second row are 1 and 1. Then the coefficients here are 1, 2, 1. Then the coefficients here are 1, 3, 3, 1, right? So we got 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. I messed up. No, I got it. Okay. Then 1, 6, 15, 20, 15, 6, 1. So what's happening is this. You're adding up. The rule of the Pascal's triangle is that the edges are always 1s. Okay, so the way you get the inner numbers, let's start with this one. You have, on the third row, you have 3 numbers. The edges have to be 1s. So how do you get this one? You add up the previous numbers on top of it. So 1 plus 1 is 2. The next row, this has to be 1, that has to be 1. So how do we get the 3? 1 and 2 is 3. How do we get this 3? 1 and 2 is 3. The next row, the 1s have to be 1s. How do we get the 4? There. 6, 4. Make sense? So what would the next row be? 1, 1. What would this one be? 7, 21, 35, 35, 21, 7, and 1. So I've gone too far. But that would be the next row coefficients. This row's coefficients is this one. It's 1 here, 6 here, 15, 20, 15, 6, and 1.
What if it were x minus y to the 6th?
X minus y to the 6th. Great question. Then you would look at this as being plus negative y, right? And so you would have this, and then this would be negative y, and since it's to the first power, that would make that negative. Then you would have negative y squared, which would make that one positive. Then the next one would be negative y cubed, which would make that negative. So what you would get is an alternating.
Okay.
Make sense?
Yes, sir.
Yep. That's the only. So if you wanted to expand, like, what is x minus 4 to the 6th, then that's really x plus negative 4 to the 6th, and you would just plug in, it would replace all your y's. You would get an alternating. Yes?
So if there was like a coefficient in front of the factor, you could do the same thing, just multiply those.
That's right. Whatever the x, so like if this was 2x, you're saying if there was a coefficient here, 2x, then this would be 2x to the 5th.
Plus 10.
Plus, and then this would be 2x to the 4th times 5. You just replace, this is just, x can be anything. Now there's another way you can do this. This right here is called Pascal's triangle. But it's kind of a ripoff because Pascal didn't come up with it. The Chinese had it a long time before Pascal. He just kind of, for some reason, got the credit. Like he gets the name on it. But there are other ways to find these numbers. You can use some stuff from statistics. It's like, have y'all ever seen like N choose R, NPR, permutations, combinations? There's a closed formula that uses factorials that you can get these without having. See, because to do this, you have to actually write out each row. You can't, like if I said, hey, what's x plus y to the 9th? You would actually need to write out the 9 rows to get to it. Where there's a shorter way using the factorials. But we'll actually talk about that when we get to series a little bit. All right. We good? Do your homework.
I'll be in the math lab from like 3 to 5. Anybody?
Wednesday is going to be a big day.
Life advice, do your homework.
Do your homework. Yep, that's a lot. There's a lot of it. Sorry to keep you late. It was worth it, though.
I love this.
You like Pascal?
So shouldn't it be called the Pascal's formula?
It shouldn't, but there's a lot of things that shouldn't be called what they are. But history and the way things are written, and there was a little bias in things, right? And if you're the first one to write it down and put your name on it, then you get credit, right?
Yeah.
Chinese had it a long time before, and they used it.
They don't call it Pascal.
They don't call it?
No,
What do they call it?
Yao-Ni triangle.
Well,